Welcome to COMP501 Foundational Programming. In this lecture, I will talk about the Big O notation. Big O notation is a mathematical way of describing how a function, the running time of an algorithm, generally behaves in relation to the input size. So basically, you look at the Big O notation, it shows the trend. The main idea behind the Big O notation is it shows the trend of the algorithm as the input size increases. That the algorithm runtime is proportional, which is linear to the input size, or does the algorithm um, running time is constant, meaning it does not matter what's the input size. In a Big O notation, all functions have the same growth rate, basically as determined by the highest order term of function. This would mean the worst case scenario are characterized by the same Big O notation. So basically, in the Big O notation, it doesn't matter if your function is say 6n squared or 10n squared. It's all n squared. We remember we want to show the trend, not really the coefficient in front of that doesn't make any difference. So given a function that describes the running time of an algorithm, the Big O notation for the function can be determined by the following rule. So this is some of the property. If f of s is the sum of the several terms, the highest order term, the one with the fastest growth rate, kept and other discarded. So if your algorithm that has say n squared plus 6n plus 3, let's just say this algorithm, then the Big O of n is n squared, because this is the fastest growth rate. If the f of s is say 6n squared, then the Big O or n here is just n squared. The coefficient doesn't matter. We remember the Big O notation just want to show the trend of the algorithm. And the trend of the algorithm, whether this is 6n squared or 100n squared, is still n squared, quadratic. So many commonly used algorithms have the running time function belong to one of the handful growth functions. And clearly, the best algorithm is the one that has a constant time complexity. But not every algorithm has the constant time complexity. And this is what keep the computer scientists up every night. They want to find a way to prove that certain type of problem can only solve with certain way. This is the best way to solve this problem, and the best way is not that good. So here are some common Big O notation. When we say Big O1, this is a constant, like a Simon statement. O log n, this is what we call logarithmic. And this is like the binary search I just showed you. It's a single loop, but inside the loop, the number of iterations keep cut in half and half and half. On is a linear search. It's called linear, similar to the linear search. And you can see the difference between these two already compared to linear search to the binary search. N log n is a log linear. This is like the merge sort and quick sort algorithm, the sorting algorithm. N squared is a quadratic. This is something that you see with the two nested loop, like in the selection sort or bubble sort. N cubed is a qubit, like 3 nested loop. And C to the n is like an exponential, like Fibonacci recursion. These can grow very quickly. So this is basically I'm showing you going from the best to worst. So how do you able to tell Big O notation? Here, this one is an O1, because all of these statements here a constant running time. There's no loop, for one thing. When you have a loop, like here, this is a O log n. This is a binary search. The loop does not go from low to high. The loop, every iteration, the loop get cut in half. So this is a divide and conquer operation. And as we saw earlier, because every time we execute a loop, every iteration, the number of elements get cut in half. The big O running time for this algorithm, binary search, is O(n). If you have a single loop, like the linear search, um, the number of operation is proportional to n, the size of the input. The merge sort is an n log n. The merge sort has, in this case, the sorting part and merging part. This part have basically log n, and this part, the merge one, have n. So between these two, you have n log n. And this is a selection sort. We will not go over this selection sort. I just want to show you. In this case, you have a nested loop. You have a 2-for loop. And when you have a nested loop and the inner loop does not do the divide and conquer in this case, you have n squared. You can look at this n squares. This one can go by n. This one can go by n. So you basically have an n by n number operation. That's why it's an n squared. And finally, the Fibonacci. This is something we did before. If for the Fibonacci number, when the n get bigger, we need to find all this previous Fibonacci number. The previous one number can grow very quickly. And some other composite function for the big O notation property. As I said earlier, any constant in front of the big O, you can drop them because we're only looking for the trend. And you also look for any you also look for the worst case scenario. So 100, which is a constant time, and O(n squared. Well, O(n squared is worse than the constant. So your runtime is O(n squared. If a product like a 10n times O(n squared, you get n cubed. But if that were like a 10 times O(n squared, this is still O(n squared. This is basically just 10 O(n squared, so which is just O(n squared. But in this case, 10n times O(n squared, the runtime would be n cubed, O(n cubed. If I have, say, 10n plus O(n squared, this is the most dominant. This is the worst case. So your runtime is O(n squared. What you see here is you want to look at the trend. And the trend is the worst case scenario of the algorithm runtime. And here just I'll give you some idea about the growth rate between log n, n log n, n squared, n cubed, and n. Given a hypothetical speaking, 10, 50, 100, log n, it grow kind of slow, all the way to 10,000, 100,000. N from 10 to 1 second. If it take for n equal to 10, take 10 microseconds. It will take 1 second for 100,000. And n log n. But I want you to take at least n squared and 2 to the n. Instead of talk about fraction of a second to few seconds, we talk about hour, year, and 2 to the n could be millennium. It might take you thousands of years just to do this algorithm if the input is so big. Of course, if the speed of the computer faster, you can also cut down the time. And that is the reason some of the algorithm become more prominent because of the computation power. It's faster now. And also people finding better way, more efficient way to do anything. Here's more like a graphically show you. The constant time is here. You can see how this growth rate work. So if I look at 4, these are the time. And I can even get the qubit time. It's way up there. And the exponential is really, really way up there. And the input side increases, the running time increase with that. And depend on the big O running time, you see how one is worse than the other. And yes, we really want to something probably along here, but there are some algorithm which is quadratic or qubit or even exponential. There are some algorithm out there like that. So from earlier example, you can see that if you see a single loop that goes from start to finish, then it's a linear ON. If you see 2 nested loops that go from start to finish, then it's a quadratic. If you see 3 nested loops that go from start to finish, not cutting in half, then it's a qubit. If you see the divide and conquer type algorithm, like the binary search, then it's a ON. If you see a divide and conquer type algorithm with loop, such as sorting, then it's a O n log n. If you see like an algorithm does not depend on the number of inputs, then it's a O1 constant. Always look at this to find the worst case scenario, and that would be the overall runtime for your program or for your algorithm. Thank you.